Tonight, we're going to take apart one of the most seductive ideas in all of science. The idea that if we could just move fast enough, the stars would finally be within reach. Traveling near the speed of light sounds like the ultimate solution. Shorten the journey to just a few years, cross the void between solar systems in a single human lifetime, and make the galaxy small enough to explore. But here's what almost nobody tells you. The faster you push a spacecraft toward the speed of light, the more the universe between the stars tries to kill you. Empty space stops being empty. Harmless particles become weapons. Faint background radiation becomes lethal. And the journey itself becomes the most dangerous environment any human being has ever entered. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Let's begin. Let us start with the distance, because the distance is the reason anyone talks about traveling near light speed in the first place. The nearest star system beyond our own sun is Alpha Centauri. It sits roughly 4.25 light years from Earth. In miles, that translates to approximately 25.6 trillion. In kilometers, approximately 41 trillion. These numbers are so large they stop meaning anything to a human brain almost immediately. So let us try to ground them in something more tangible. Light is the fastest thing in the universe. It moves at approximately 186,000 miles per second, or roughly 300,000 kilometers per second. Nothing with mass has ever been observed to travel that fast. Only individual subatomic particles in controlled accelerator environments have been pushed close. Light covers the distance from the Earth to the Moon in about 1 1/3 seconds. It reaches the Sun in roughly 8 minutes. It crosses the entire diameter of our solar system, from one edge of the Oort cloud to the other, in perhaps a year or two, depending on where you draw the boundary. And it takes 4 years and roughly 3 months just to reach Alpha Centauri. That gap between crossing our own solar system and reaching the nearest neighboring star is where the entire problem of interstellar travel lives. The stars are not just far away. They are far away on a scale that renders every other distance humanity has ever dealt with effectively meaningless. Every ocean we have crossed, every continent we have mapped, every orbit we have achieved, all of it fits comfortably inside a tiny fraction of the distance to the nearest star. Now let us see how our actual spacecraft compare. Voyager 1, launched in 1977, is the most distant human-made object in existence. It has been flying through space for nearly 50 years and has covered approximately 15 billion miles. It is currently traveling at roughly 38,000 miles per hour. That is fast by any human standard. At that speed, you could cross the entire continental United States in about 4 minutes. But at that speed, the journey to Alpha Centauri would take approximately 73,000 years. 73,000 years. The entirety of recorded human history fits inside the last 5,000 years. Voyager 1 would need more than 14 times that span just to reach the next star over. The Parker Solar Probe, launched in 2018, holds the record as the fastest spacecraft humanity has ever built. At its closest approach to the Sun, it reaches approximately 430,000 miles per hour, roughly 11 times faster than Voyager 1. And yet, even at that speed, Alpha Centauri is still roughly 6,700 years away, still measured in millennia. So when scientists and engineers talk about reaching another star within any time frame, that a human being could survive, they are not talking about building slightly better versions of the rockets we already have. They are not talking about incremental improvements. They're talking about speed so far beyond current capability that the gap is almost absurd. To cross interstellar distance in a single human lifetime, you would need a significant fraction of the speed of light. At 1%, Alpha Centauri is still over 400 years away. You would need 10, 20, 50% or more. At 10% of the speed of light, about 30,000 kilometers per second, Alpha Centauri is roughly 42 years away. At 50%, roughly 8.5 years. At 90%, under 5 years of Earth time. The math is seductive. Push the speed higher and the travel time drops. Push it high enough and the stars become reachable within a human generation. This is the dream that has fueled a century of speculation about interstellar travel. It has shaped science fiction, inspired engineering studies, and motivated real research programs. Build a ship fast enough and the galaxy opens up. The distance stops being the problem. The speed is the solution. But here is where the physics introduces a correction that changes everything about this picture. And it is not a small correction. It is a fundamental one. No spacecraft carrying mass can ever actually reach the speed of light. Not almost. Not with enough energy. Not with a better engine or a larger fuel supply or some future technology we have not invented yet. The speed of light is not an engineering barrier waiting for the right breakthrough to shatter it. It is a structural limit woven into the fabric of space-time itself, and it applies to every particle, every object, every ship with mass in the entire universe, without any known exception. This comes directly from Einstein's theory of special relativity, published in 1905. One of the central results of the theory is that as an object with mass accelerates closer and closer to the speed of light, its kinetic energy does not increase in the simple, proportional way our everyday experience would suggest. At low speeds, the kind humans deal with in daily life, kinetic energy follows the classical formula most people learn in school. Half the mass times the velocity squared. Double your speed, and you quadruple the energy. Triple the speed, and the energy goes up 9 times. This works beautifully for cars, bullets, baseballs, aircraft, rockets, anything moving at speeds that are a tiny fraction of the speed of light, and all human-scale speeds are a tiny fraction of the speed of light. A commercial aircraft moves at about 1/1,000,000th of light speed. Even the Parker Solar Probe at its peak is moving at less than 1/1500th of light speed. At these velocities, the classical formula is virtually perfect, but as you push toward a substantial fraction of the speed of light, the classical formula begins to fail. The true kinetic energy of a moving object is governed by a relativistic relationship that includes something called the Lorentz factor. The Lorentz factor, usually represented by the Greek letter gamma, is defined as 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. At low speeds, gamma is extremely close to 1, and the relativistic formula collapses to the familiar classical version. No meaningful difference, but as velocity climbs toward the speed of light, gamma begins to grow, and it grows in a way that accelerates as speed increases. At 10% of light speed, gamma is about 1.005. The correction to kinetic energy is less than 1%, barely noticeable. At 50% of light speed, gamma rises to approximately 1.155. Kinetic energy is now about 15.5% higher than what the classical formula would predict. Still not dramatic, but measurable and real. At 90% of light speed, gamma reaches roughly 2.29. The kinetic energy is now more than double what the simple formula predicts. The classical formula is no longer remotely accurate. At 99% of light speed, gamma is approximately 7.09. Kinetic energy is now about 6 times the rest mass energy of the object itself. The object carries more energy in its motion than is contained in its entire mass, converted to energy via E equals mc squared. At 99.9%, gamma rises to about 22.4. And as velocity approaches the speed of light exactly, gamma approaches infinity. The kinetic energy required to push a massive object to light speed would be infinite, not impractically large, not theoretically staggering, infinite. It cannot be done. This is not a statement about current technology. It is a statement about the structure of the universe. This is why every honest discussion of interstellar travel for a spacecraft with mass, and that includes every discussion involving human beings, is a discussion about traveling near the speed of light. Not at it. Never at it. The real scenario is always some fraction. 90%, 99%, perhaps 99.9, but never 100. That last fraction of a percent is unreachable in principle, not just in practice. And this matters not just as a technical footnote. It matters because of what the Lorentz factor tells us about what happens to the energy environment around a ship as speed increases. Because that energy does not stay abstract. It becomes physical. It becomes real. And it becomes dangerous in ways that almost no popular treatment of interstellar travel bothers to explain. Let us make this concrete, because the numbers are what make this terrifying. Take a 1 kilogram object. That is roughly the mass of a hardcover book or a litre of water. A perfectly ordinary, harmless amount of matter. Now accelerated at 10% of the speed of light. About 30,000 kilometers per second. At that speed, the kinetic energy of that 1 kilogram object is approximately 450 trillion joules. To put that in more familiar destructive terms, it is roughly equivalent to 107 kilotons of TNT. For reference, the atomic bomb dropped on Hiroshima in 1945 released approximately 15 kilotons of energy. So a single kilogram moving at 10% of light speed carries the kinetic energy of roughly 7 Hiroshima bombs, 1 kilogram, at just 10% of light speed. And 10% is the low end of what serious interstellar proposals typically require. Now push the speed higher. At 50% of light speed, accounting for relativistic effects, that same 1 kilogram object carries approximately 14 quadrillion joules of kinetic energy. That is roughly 3.3 megatons of TNT equivalent, more than 200 Hiroshima bombs, concentrated in a single kilogram of anything. At 90% of light speed, the kinetic energy climbs to approximately 117 quadrillion joules, roughly 28 megatons of TNT. That is in the range of the most powerful thermonuclear weapons ever detonated in testing during the Cold War. At 99% of light speed, 1 kilogram carries roughly 550 quadrillion joules, approximately 130 megatons of TNT, more than twice the yield of the largest nuclear device ever built. And here is the critical point. This is not 1 kilogram of explosive. This is not 1 kilogram of nuclear fuel. This is 1 kilogram of absolutely anything. A book, a rock, a bottle of water, a clump of frozen mud. At these speeds, the chemical composition is irrelevant. The material is irrelevant. What matters is mass and velocity. And at relativistic velocities, even a trivially small mass becomes a weapon of extraordinary destructive power. But you do not need a kilogram for the danger to be real. You do not need anything close to a kilogram. Consider a dust grain, not a pebble, not a stone, a single particle of interstellar dust, the kind that drifts invisibly in the space between stars, with a mass of roughly 1 milligram, 1,000th of a gram. You could fit thousands of them on your fingernail. At 10% of light speed, that 1 milligram grain carries approximately 450 million joules of kinetic energy. That is the energy equivalent of roughly 107 kilograms of TNT. Over 200 pounds of high explosive, concentrated in a particle far too small to see with the naked eye. At 50% of light speed, the same milligram grain carries energy equivalent to about 3 1/3 metric tons of TNT. At 90%, approximately 28 metric tons. Now consider a pebble, a small stone with a mass of about 1 gram, the weight of a paperclip. At 10% of light speed, that pebble carries roughly the energy of 107 metric tons of TNT. At 50%, it reaches the energy equivalent of about 3.3 kilotons of TNT. That is comparable to a small tactical nuclear weapon. One pebble. The physics here is absolutely relentless. Kinetic energy at relativistic speeds does not scale the way everyday experience trains you to expect. The relationship between speed and energy starts gently, almost linearly at low velocities, and then the Lorentz factor bends the curve violently upward as velocity climbs. Every additional percentage point of light speed you add comes with a disproportionate increase in collision energy, and that increase does not plateau. It does not level off. It keeps rising, faster and faster, approaching infinity as velocity approaches the speed of light. And this is the trap embedded in the heart of near light speed travel. Speed is supposed to be the solution to interstellar distance. Speed is what makes a 4 light-year journey achievable in a human lifetime. Speed is the variable you push higher to make the stars reachable. But every increment of speed you add does not just shorten the trip. It simultaneously loads the spacecraft with kinetic energy. It raises the destructive potential of every possible collision the ship could have with anything in its path. It transforms the relationship between the ship and its environment from something manageable into something violent and extreme. At the speeds of our fastest current spacecraft, hitting a grain of dust in space is insignificant. At 10% of light speed, it is a serious event. At 50%, it is a potential catastrophe. At 90%, it is an explosion. And this raises an obvious and urgent question. If the collision energy rises so dramatically with speed, then the critical issue becomes what the ship is actually going to encounter during an interstellar journey. What is out there in the space between stars that the ship might hit? Most people assume the answer is nothing. Space is a vacuum. The void between the stars is empty. There is nothing out there to collide with. So the explosive kinetic energy at relativistic speed is a theoretical concern with no practical consequence. This assumption is wrong. It is dangerously, fundamentally wrong. The space between stars is not empty. It has never been empty. It appears empty because what it contains is sparse and invisible to the naked eye. But it contains matter. Gas atoms, primarily hydrogen and helium, spread thinly across the light years. Dust grains, microscopic particles of silicate and carbon, scattered among the gas, occasional heavier atoms, trace amounts of molecules in denser regions. The interstellar medium, the material that fills the space between stars within our galaxy, contains on average roughly 1 hydrogen atom per cubic centimeter. That density is not uniform. In hot, diffuse regions between the spiral arms, it can drop to as low as 1/100th of an atom per cubic centimeter. In denser clouds and nebulae, it rises to thousands or millions. But the average through which an interstellar spacecraft would travel is approximately 1 atom per cubic centimeter, with some helium and traces of heavier elements mixed in. By any terrestrial standard, this is an astonishing vacuum. The air at sea level contains roughly 30 billion molecules per cubic centimeter. A typical high vacuum chamber on Earth still contains roughly 10 billion molecules per cubic centimeter. Interstellar space is trillions of times emptier than anything we can create artificially. The intuition that space is empty is not entirely wrong by everyday standards. But a spacecraft traveling at a significant fraction of light speed sweeps through enormous volumes of that near vacuum every second. At 10% of light speed, about 30,000 kilometers per second, a ship with a frontal cross-section of just 10 square meters sweeps through approximately 300 trillion cubic centimeters of space every single second. At 1 hydrogen atom per cubic centimeter, that is 300 trillion hydrogen atoms impacting the front of the ship every second. At 50% of light speed, the rate rises to roughly 1.5 quadrillion atoms per second. At 90%, close to 3 quadrillion per second. And each one of those atoms is not drifting gently into the hull the way a molecule of air brushes against your skin on a calm day. Each one is striking with the energy of a relativistic particle, moving at the same speed as the ship, but in the opposite direction. At these velocities, each individual hydrogen atom carries enough kinetic energy to ionize thousands of other atoms on impact, penetrating into whatever material it strikes and depositing destructive energy as it goes. And the energy per atom climbs sharply with speed, crossing thresholds that transform the interaction from chemistry into something far more violent. The ship is flying through a particle beam, not a narrow, carefully focused laboratory beam, but a wide, continuous, inescapable bombardment of relativistic hydrogen covering the entire forward face of the spacecraft. And it does not stop. It does not thin out. It does not take a break. It continues for every second of every hour of every day for the entire duration of the journey, which at these speeds is still measured in years. And that is just the hydrogen. The interstellar medium also contains helium, roughly 10% by number of atoms. Helium atoms are 4 times heavier than hydrogen, so each helium impact carries proportionally more kinetic energy. There are trace amounts of heavier elements as well. Carbon, nitrogen, oxygen, iron. Each heavier atom hits harder, and scattered among the gas are dust grains. Tiny particles of silicate and graphite, most of them smaller than a micrometer across, but some reaching several micrometers. We have already seen what happens when a milligram dust grain strikes at relativistic speed. The interstellar medium contains these grains at a density of roughly 1 grain for 300,000 to 1 million cubic meters, depending on the region. That sounds sparse. Over a journey of 4 light years, it adds up to a large number of impacts. The space between stars is not a wall. It is not a debris field. It is not an asteroid belt. It is not anything you can see coming or steer around. It is an invisible, continuous, diffuse presence that a relativistic spacecraft flies through for years on end, sweeping up gas and dust the entire way. And at the speeds required to make interstellar travel practical, that tenuous material transforms from an irrelevant trace into a relentless bombardment that threatens every surface, every system, and every occupant of the ship. This is the part of near light speed travel that most discussions leave out. The speed that solves the distance problem creates a completely different problem. It turns the thinnest, most diffuse material in the known universe into a continuous stream of relativistic projectiles aimed squarely at the hull. It transforms empty space into something that behaves, from the ship's perspective, like flying face first into the beamline of a particle accelerator that stretches across 4 light years and never shuts off. And we have not yet talked about what that bombardment actually does to the ship. We have not talked about what happens when trillions of relativistic hydrogen atoms per second slam into a hole that is supposed to keep human beings alive on the other side. We have not talked about the heat those impacts generate, or the radiation they produce, or the secondary particles that cascade through the shielding material with every collision. We have not talked about what happens to the hull itself over months and years of continuous erosion at speeds where every atom hits like a bullet. The emptiness between the stars is an illusion, and at relativistic speed, it is a lethal one. What those impacts actually do to a ship, and why they make near light speed travel far more dangerous than almost anyone realizes, is what comes next. To understand what the interstellar medium does to a spacecraft at relativistic speed, you first have to abandon a piece of intuition that works perfectly well in everyday life, but becomes completely misleading at these velocities. In normal experience, gas is gentle. Air pushes against your hand when you wave it. Wind buffets a car on the highway. These are interactions at a few dozen miles per hour, where individual atoms carry negligible energy. Even at supersonic speed, the interaction between vehicle and atmosphere is a matter of friction and pressure, manageable with the right materials. At the speed of a re-entering spacecraft, roughly 17,000 miles per hour for low Earth orbit, the interaction becomes violent. The compressed air ahead of the capsule heats to thousands of degrees, producing the searing plasma trail visible during re-entry. This is dangerous and requires careful thermal protection. But even at re-entry speed, the individual atoms in the atmosphere are carrying only a few electron volts of kinetic energy each. That is the energy scale of ordinary chemistry. Enough to excite atoms, break some molecular bonds, heat surfaces. Serious, but manageable. Now consider what happens to those interactions at a significant fraction of the speed of light. At 10% of light speed, each hydrogen atom in the interstellar medium strikes the spacecraft with roughly 4.5 million electron volts of energy. That is not chemistry anymore. That is nuclear physics. Each individual hydrogen atom hits with the energy of an alpha particle emitted during radioactive decay, and there are hundreds of trillions of them arriving every second across the forward face of a human-scale ship. At 20% of light speed, the energy per hydrogen atom rises to roughly 19 million electron volts. This is the lower threshold of the energy range used in medical particle therapy, where focused beams of protons are aimed at tumors to shatter molecular bonds in living tissue. Every single hydrogen atom in the interstellar medium is now arriving at the ship with enough energy to penetrate millimeters into solid material and destroy molecular structures as it goes. At 50% of light speed, Each atom carries over 100 million electron volts. This is the energy range of the particles circulated in medium energy physics research accelerators. Each individual hydrogen impact deposits enough energy to ionize thousands of atoms in whatever material it strikes, producing a cascade of secondary particles that penetrate deeper into the hull than the original atom itself. At 90% of light speed, the energy exceeds 1 billion electron volts per atom. This is the energy scale of the main injector ring at major particle physics laboratories. Each hydrogen atom from the interstellar medium is now a cosmic ray equivalent, carrying enough energy to pass entirely through thin shielding, producing showers of secondary radiation as it goes. The transformation is total. At rest relative to the spacecraft, the interstellar medium is a sparse collection of harmless atoms, so thin it barely qualifies as matter. In the reference frame of a ship moving at relativistic speed, it is an unbroken stream of high-energy particles, indistinguishable from the output of a radiation source. The ship is not flying through gas. It is flying through a directed beam of ionizing radiation that covers the entire forward surface and continues without interruption for the entire journey. And the effects of this bombardment are not speculative. They have been studied in detail by physicists working on the problem of relativistic spacecraft survival, including researchers affiliated with the NASA Starlight program and the Breakthrough Starshot initiative. A research paper published by Huang and colleagues in the Astrophysical Journal examined the interaction between a relativistic spacecraft and the interstellar medium at speeds up to and beyond 20% of light speed. Their analysis addressed both gas bombardment and dust grain impacts, and the findings are sobering. For gas bombardment, the dominant damage mechanism is not simple surface heating, although surface heating does occur. The dominant mechanism is something called track formation. When a relativistic atom, particularly a heavier element like carbon, oxygen, or iron, penetrates the surface of the spacecraft, it plows through the material in a straight line, ionizing and displacing atoms as it goes. It leaves behind a narrow cylindrical track of disrupted material, atoms knocked out of their lattice positions, molecular bonds shattered, local temperature spiked far above the surrounding material. Each track is tiny, perhaps a few nanometers wide, but over hours and days and months of continuous bombardment by trillions of atoms per second, these tracks accumulate. They overlap. They weaken the crystalline structure of the whole material from the inside, creating a layer of progressively degraded, embrittled material on the forward face of the ship. Heavier elements in the interstellar medium do disproportionate damage because track formation scales with the square of the atomic number of the incoming particle. An iron atom with an atomic number of 26 produces a track roughly 676 times more damaging per unit length than a hydrogen atom. Iron is rare in the interstellar medium, making up far less than 1% of all atoms. But over the course of a journey spanning light years, even rare heavy elements accumulate enough impacts to contribute meaningfully to hull degradation. A separate study by Drobny and colleagues, also working within the NASA Starlight collaboration, investigated a damage mechanism that is in some ways even more insidious than track formation. This is the problem of gas accumulation. When relativistic hydrogen and helium atoms strike the spacecraft hull, they do not all pass through cleanly. Many of them come to rest inside the material, embedded at a characteristic depth that depends on their energy and the density of the hull. At 20% of light speed, hydrogen atoms penetrate to a depth of roughly 1 to several millimeters in most solid materials before stopping. Helium atoms stop at a similar depth, and once they stop, they stay. They are implanted in the material, lodged between the atoms of the hole's crystalline lattice. Over time, these implanted gas atoms accumulate. Hydrogen and helium do not bond well with the metallic or ceramic materials likely to be used in spacecraft construction. They do not integrate into the lattice. Instead, they cluster together, forming tiny bubbles of trapped gas within the solid material. As more atoms are implanted, these bubbles grow. The internal pressure rises, and eventually, the pressure becomes high enough to deform the surrounding material. The result is a phenomenon well known in nuclear engineering and material science. It is called blistering. The trapped gas inflates pockets beneath the surface of the material, raising visible blisters that weaken the structural integrity of the hull. When these blisters rupture, they eject fragments of hull material outward in a process called exfoliation. The surface literally peels away, layer by layer, eroded from within by the gas it has been forced to absorb. This is not theoretical. Blistering and exfoliation are routinely observed in the walls of nuclear fusion reactors, where hydrogen isotopes are implanted into the containment vessel walls by the plasma. The process is well documented, well studied, and well understood. The difference is that a fusion reactor wall can be inspected, repaired, and replaced. A spacecraft hull 4 light years from the nearest repair facility cannot. Drobny and colleagues calculated that for a spacecraft traveling at 20% of light speed through a typical interstellar medium density, the erosion rate from gas accumulation, blistering, and exfoliation could remove a meaningful thickness of hull material over the course of a journey to Alpha Centauri. The exact rate depends on the hull material, the gas density along the flight path, and the speed, but the conclusion is clear. The ship is being eaten alive from the front. Not by collisions with large objects, not by dramatic impacts, by the slow, relentless implantation of individual atoms that the ship cannot avoid, cannot deflect without enormous effort, and cannot survive indefinitely without some form of sacrificial shielding or continuous hull replenishment. And we have not yet talked about dust. Interstellar dust grains are far less numerous than gas atoms, but they are far more massive per particle. A typical interstellar dust grain is a microscopic solid particle, usually composed of silicate compounds or carbon, with a diameter ranging from a few nanometers up to about 1 micrometer. The larger grains have masses in the range of a trillionth to a billionth of a gram, extraordinarily small by everyday standards. But at relativistic speed, velocity enters the kinetic energy formula squared, then gets amplified further by the Lorentz factor. When a dust grain strikes a surface at relativistic speed, the collision does not resemble anything from ordinary experience. The kinetic energy of the grain is so far above the binding energy of the atoms within it that the grain does not behave as a solid object on impact. It does not bounce. It does not embed itself in the hull like a bullet in a wall. Instead, the grain and the surface material at the point of impact both instantly ionize. The atoms of the grain and the atoms of the hull are stripped of their electrons and converted into a superheated plasma in a fraction of a nanosecond. The energy of the impact radiates outward from the collision point as a shock wave through the whole material, melting and vaporizing a volume many times larger than the grain itself. Huang and colleagues modeled this process in detail. They found that a single dust grain impact at 20% of light speed creates a crater on the whole surface whose diameter is many times larger than the grain. The crater forms through explosive vaporization of both the grain and the surrounding whole material. The vaporized material expands outward as a plasma jet, carrying whole mass away with it. Each impact removes a small but measurable amount of whole material, and over the course of a full interstellar journey, the cumulative erosion from dust impacts alone is significant. Their calculations showed that for a spacecraft traveling at 20% of light speed to Alpha Centauri, dust bombardment could erode a surface layer of material on the order of a fraction of a millimeter to several millimeters in thickness, depending on the whole material and the dust density encountered. For a gram-scale nanocraft of the kind envisioned by Breakthrough Starshot, this erosion is potentially mission-ending. For a larger crewed spacecraft with a thicker hull, the erosion is survivable in principle, but demands either very thick sacrificial shielding at the front of the ship or some method of continuously replenishing the forward surface. And the damage is not limited to erosion. Each dust grain impact also produces a burst of electromagnetic radiation. The superheated plasma at the impact site emits across a wide spectrum, from infrared through visible light into ultraviolet and X-rays. This radiation propagates through the whole material and into the interior of the spacecraft, contributing to the overall radiation dose experienced by any equipment or crew behind the forward shielding. A single impact might produce a negligible radiation pulse. Thousands of impacts over the course of a journey produce a cumulative dose that must be accounted for in the overall radiation budget of the mission. There is another class of dust impact that deserves separate attention because it represents a different order of threat entirely. The interstellar medium contains not just micrometer-scale grains, but also larger particles. Fragments of rock and ice ejected from planetary systems, debris from ancient collisions, material shed by comets passing through the interstellar void. These particles are far rarer than microscopic dust, but they are far more massive. A grain the size of a sand particle, perhaps a tenth of a millimeter across, might have a mass of a few micrograms. A pebble a millimeter across might weigh a milligram or more. We have already seen what happens when a milligram grain strikes at relativistic speed. The numbers were already alarming at 10% of light speed. At higher velocities, they become extreme. A single sand grain-sized particle striking at 50% of light speed releases energy on the order of the detonation of a large industrial explosive charge. A pebble at the same speed releases energy comparable to the yield of a cruise missile warhead. At relativistic speed, there is no practical way to detect these particles in advance. The ship is covering tens of thousands of kilometers every second. Light reflected or emitted by a small particle ahead of the ship has almost no time to reach the ship's sensors before the ship itself arrives at the particle's location. For a grain a millimeter across, floating in the void directly ahead, the detection window at 50% of light speed is measured in fractions of a microsecond. No sensor can detect, identify, and characterize an object that's small in that amount of time. No maneuvering system can alter the ship's trajectory fast enough to avoid it. The ship hits whatever is in its path. There's no dodging. There is no evasion. There is only the statistical probability of encountering a particle of a given size over the distance traveled, and the engineering question of whether the ship can survive the impact if it does. For microscopic dust, the answer is potentially yes, with sufficient shielding. For sand grain-sized particles, the answer depends entirely on how thick the forward shielding is and how much of the impact energy it can absorb before the shock wave reaches critical systems. For anything larger than a few millimeters, the answer at relativistic speed is almost certainly no. No practical amount of shielding can absorb that much energy concentrated in that small an area without catastrophic structural failure. The probability of hitting a larger particle is lower than the probability of hitting microscopic dust. The interstellar medium is sparse, and larger particles are rarer. But the journey is long. 4 light years is an enormous distance. The ship sweeps through a vast corridor of space over the course of the trip, and the statistical tail of rare but catastrophic impacts extends across that entire corridor. Over a 4 light-year journey at relativistic speed, the probability of encountering at least one particle large enough to cause serious damage is not negligible. It is a real risk that cannot be engineered away with certainty. Let us step back and consider the total picture of what the forward face of a relativistic spacecraft experiences during an interstellar crossing. Every second, hundreds of trillions to quadrillions of hydrogen and helium atoms slam into the hole at energies ranging from millions to billions of electron volts per atom. Each atom deposits ionizing energy as it penetrates, producing radiation tracks in the whole material and generating secondary particles that cascade deeper into the structure. Many of these atoms come to rest inside the hull, where they accumulate over time, forming gas bubbles that blister and exfoliate the surface from within. Simultaneously, dust grains strike at intervals measured in seconds to minutes, each impact explosively vaporizing a small volume of whole material, each crater slightly deeper than the last because the surface has already been weakened by gas bombardment and track damage. Each dust impact produces a pulse of radiation that adds to the continuous dose from gas bombardment. And occasionally, very rarely but inevitably over a journey of light years, a larger particle hits. A sand grain, a pebble, a fragment of something that was once part of a distant solar system, now drifting in the void. When it strikes, the energy release is catastrophic for the local area of the hull. This is not a single hazard. It is a layered, compounding set of hazards that operate simultaneously and continuously for the entire duration of the flight. The gas bombardment is constant and inescapable. The dust erosion is persistent and cumulative. The rare large impacts are unpredictable and potentially unsurvivable. And all of them grow worse as speed increases, because higher speed means higher energy per particle, higher flux rate as the ship sweeps through more volume per second, deeper penetration of the hull, faster erosion, more intense secondary radiation. The relationship between speed and danger is not linear. It is not even simply quadratic, as the classical kinetic energy formula might suggest. At relativistic velocities, the Lorentz factor bends the curve upwards so aggressively that each additional percentage point of light speed purchased with enormous expenditures of propulsion energy comes with a disproportionate increase in the severity of every impact hazard the ship faces. This creates a fundamental tension at the heart of interstellar mission design. You need speed to cross the distance in a reasonable time, but the speed you need transforms the medium you must cross from an irrelevant trace of matter into a continuous assault on the structural integrity, the radiation environment, and the thermal balance of the ship. There is no way around this. There is no trajectory that avoids the interstellar medium because the interstellar medium is everywhere. There are denser and less dense regions, but there is no path between any two stars in our galaxy that passes through truly empty space. Even in the lowest density regions between the spiral arms, the gas density is sufficient that at relativistic speed, the bombardment is significant. In the local interstellar cloud, the region of slightly enhanced density through which our own solar system is currently passing, the density is modestly higher than the galactic average, and any ship departing from our solar system would pass through it during the early phase of the journey. You cannot outrun the problem because the problem is caused by the speed itself. Slowing down reduces the danger but defeats the purpose of the mission. Speeding up shortens the trip but intensifies every hazard proportionally, and then some. And the particle bombardment is not the only consequence of relativistic velocity. It is, in a sense, the most direct and intuitive one, the one most easily understood as a collision problem. But there are other effects that operate on different physical principles and create additional layers of danger that compound on top of the impact hazards. The radiation environment inside the ship is not determined solely by the particles that strike the hull. It is determined by what those particles produce when they interact with the hull material. When a relativistic hydrogen atom enters the forward shielding and begins to slow down, it does not simply stop and sit quietly in the lattice. As it decelerates through the material, it radiates energy. This process, called bremsstrahlung, German for break-in radiation, produces high-energy photons, X-rays and gamma rays that propagate through the shielding in all directions, including backward toward the interior of the ship. The intensity of bremsstrahlung radiation depends on the energy of the incoming particle and the density and atomic number of the shielding material. Higher energy particles produce more bremsstrahlung. Denser, heavier shielding materials produce more bremsstrahlung per unit of stopping power. This creates a paradox for shield designers. You want thick, dense shielding to stop the incoming particles, but thick, dense shielding produces more secondary radiation as it does its job. The shield that protects you from the primary beam simultaneously generates a secondary radiation field of its own. Research from the NASA Starlight collaboration has quantified this effect for spacecraft traveling at 20% of light speed. At that velocity, relativistic protons from the interstellar medium penetrate to depths on the order of millimeters in typical solid materials before stopping. Electrons, being much lighter, stop within nanometers of the surface. Both produce bremsstrahlung photons as they decelerate. The resulting photon field inside the shielding depends on the material composition and thickness, but for any realistic shield configuration, a measurable dose of secondary radiation reaches the interior of the spacecraft. Let us walk through what actually happens inside the shield, step by step, because this is where the intuition that thicker armor means better protection begins to break down. A single relativistic proton, one hydrogen atom stripped of its electron by the violence of the collision, enters the forward face of the shield traveling at 20% of light speed. It carries roughly 19 million electron volts of kinetic energy. As it plunges into the shield material, it begins to interact with the atoms of the shield. It does not stop instantly. It decelerates over a distance of roughly 1 to several millimeters, depending on the density of the material. And as it decelerates, it does two things simultaneously. First, it ionizes the atoms along its path. it knocks electrons free from the shield material's atoms, leaving a trail of disrupted atomic bonds and displaced lattice atoms behind it. This is the track formation mechanism we discussed earlier. The energy deposited along this track heats the local material and damages its structure. Second, and this is the part that makes shielding design so treacherous, the proton radiates photons as it decelerates. Every time a charged particle changes velocity, it emits electromagnetic radiation. The more abruptly it decelerates, the higher the energy of the emitted photons. A proton carrying millions of electron volts, stopping within millimeters of dense material, emits photons in the X-ray and gamma-ray range. These bremsstrahlung photons radiate outward from the proton's stopping point in all directions, including backward, deeper into the shield, toward whatever the shield is supposed to be protecting. Now here is the problem. The proton itself was stopped by the shield. It went a few millimeters and came to rest. Mission accomplished, from the perspective of stopping the primary particle. But the bremsstrahlung photons it produced during its last few millimeters of travel are not charged. They are photons, electromagnetic radiation, and they do not interact with matter the same way a charged proton does. They are far more penetrating. A gamma-ray photon produced inside the shield can travel centimeters or even tens of centimeters through dense material before being absorbed. Some of them will pass entirely through the shield and emerge on the other side, carrying their energy into the interior of the spacecraft. And it is not one proton, it is hundreds of trillions of them per second, each one stopping inside the shield, each one producing its own small spray of bremsstrahlung photons. Each spray contributing to a continuous, diffuse field of secondary X-ray and gamma-ray radiation that permeates the entire shield volume and leaks through to the interior. The total intensity of this secondary field depends on three variables: the energy of the incoming protons, which is set by the ship's speed and cannot be changed without changing the mission profile; the density and atomic number of the shield material, which determines how quickly the protons stop and how much bremsstrahlung they produce per unit of deceleration; and the thickness of the shield, which determines how much of the secondary radiation is reabsorbed before it reaches the interior. This is where the paradox emerges. A thicker shield absorbs more secondary photons before they reach the crew, but it also means protons are stopping inside a larger volume, producing bremsstrahlung over a wider region, and some of those photons are generated close enough to the interior face that they escape before reabsorption. Worse, denser, higher atomic number materials improve stopping power, but increase the bremsstrahlung yield per proton because heavier atoms convert kinetic energy into photon radiation more efficiently. You can optimize the shield composition. Lower atomic number materials like polyethylene or lithium hydride produce less bremsstrahlung per proton than high atomic number materials like lead or tungsten. But lower atomic number materials are also less effective at stopping protons in a short distance, meaning the protons penetrate deeper before stopping, potentially getting closer to the interior before they produce their secondary radiation. The shield designer is caught between two curves. One material type stops particles efficiently but generates intense secondary radiation. The other generates less secondary radiation but lets particles penetrate further before stopping them. There is no material that solves both problems simultaneously. There are only composite shield designs that attempt to balance the two failure modes, layering different materials to stop primary particles early while absorbing secondary photons before they reach the protected volume. These composite designs are heavier and more complex than single material shields, and their effectiveness depends on the incoming particle energy, which changes with ship speed. The net result is that the radiation field inside a shielded relativistic spacecraft is not zero. It is a reduced but non-zero dose of secondary radiation that persists as long as the ship is moving through the interstellar medium. The shield is not a wall that blocks danger. It is a converter that transforms one kind of danger, a stream of relativistic protons, into a different kind of danger, a diffuse bath of high-energy photons, and the conversion is never perfectly efficient. Some radiation always leaks through. The question for mission planners is how much and whether the crew can survive the cumulative dose over the duration of the journey. For a tiny, uncrewed probe like those envisioned by the Starshot concept, this secondary radiation is a threat to electronic components. Ionizing radiation degrades semiconductor devices over time, causing bit flips in memory, threshold shifts in transistors, and eventual failure of circuits. A probe traveling at 20% of light speed for 20 years must be hardened against this cumulative radiation dose or accept a progressively increasing failure rate in its onboard systems. For a crewed spacecraft, the implications are far more severe. Human tissue is sensitive to ionizing radiation at doses well below what would damage hardened electronics. The continuous bremsstrahlung field produced by the forward shield, combined with the direct radiation from particles that penetrate the shield entirely, creates a whole body dose rate that depends critically on speed, shielding thickness, and journey duration. And at the speeds required for practical interstellar travel, the numbers become alarming. A published analysis titled Speed Kills by Edelstein and colleagues examined the radiation dose that would be received by passengers aboard a spacecraft traveling through the interstellar medium at various fractions of light speed. Their conclusion was stark. At speeds above approximately 50% of light speed, the radiation dose from interstellar hydrogen bombardment alone, not counting dust impacts, not counting cosmic rays, not counting secondary radiation, exceeds lethal thresholds for human beings even with substantial shielding. The hydrogen atoms in the interstellar medium, each one carrying hundreds of millions of electron volts of kinetic energy, collectively deliver a radiation dose measured in grays per second that would kill an unshielded human in minutes and overwhelm any realistic passive shielding configuration within hours to days. Their analysis suggested an effective speed limit for crewed interstellar travel. Below approximately 50% of light speed, the radiation dose from interstellar hydrogen is manageable with heavy shielding, though still significant. Above 50%, the dose becomes lethal regardless of shielding, because the energy per particle is high enough that the secondary radiation produced inside the shield itself becomes the dominant hazard. You cannot make the shield thick enough without making the ship too massive to accelerate. And thicker shielding produces more bremsstrahlung, so beyond a certain point, adding more shielding actually increases the interior dose rather than decreasing it. This is a speed limit imposed not by engineering limitations or fuel constraints, but by the physics of particle interactions with matter. It is as fundamental as the speed of light itself, though for a different reason. The speed of light is unreachable because a kinetic energy approaches infinity. 50% of light speed may be the practical ceiling, because above it, the interstellar medium becomes a radiation source that no passive shield can adequately attenuate. And all of this analysis considers only the interstellar medium that the ship runs into along its path. It does not yet account for the radiation that is already present in space and that changes character as the ship's velocity increases. It does not account for cosmic rays, which arrive from every direction in the galaxy and whose apparent distribution shifts dramatically in the reference frame of a fast-moving ship. And it does not account for the faint glow that fills all of space, the cosmic microwave background, which at rest is a harmless bath of low-energy photons, but which at extreme velocities transforms into something far more energetic and far more dangerous. These additional radiation sources layer on top of the interstellar medium bombardment, compounding the total dose, complicating the shielding problem, and narrowing further the window of speeds at which a crude interstellar mission could survive the journey. The particle gauntlet of dust and gas is not the whole story. It is the first layer, and behind it stand more layers, each one connected to the same root cause. The speed that makes the stars reachable is the speed that makes the journey lethal. What those additional radiation sources look like, why shielding against all of them simultaneously may be one of the hardest engineering problems ever conceived, and why the ship cannot simply point sensors forward and steer around the danger, is what comes next. The interstellar medium is not the only radiation source a relativistic spacecraft has to survive. It is the most direct one, the one created by the ship's own motion through matter. But there are radiation fields that already exist in space, fields that fill the entire universe, fields that a stationary observer would barely notice, but that change character dramatically when the observer is moving at a significant fraction of light speed. And the way they change makes the shielding problem not just harder, but potentially unsolvable with any engineering approach currently imaginable. Start with cosmic rays. Cosmic rays are high-energy charged particles, mostly protons and atomic nuclei, that travel through the galaxy at close to the speed of light. They originate from violent astrophysical events. Supernova remnants, the expanding shells of gas left behind when massive stars explode, are the primary source. The shock waves from these explosions accelerate charged particles to extraordinary energies, flinging them across the galaxy where they bounce off magnetic field lines and eventually fill interstellar space in all directions. On Earth, we are largely protected from cosmic rays by two layers of defense. The planet's magnetic field deflects many of the incoming charged particles, channeling them toward the poles where they produce the aurora. And the atmosphere absorbs most of what the magnetic field misses. By the time a cosmic ray reaches the surface, it has typically collided with atmospheric molecules at high altitude, shattering into a shower of secondary particles that spread out and lose energy before reaching the ground. The cosmic ray dose at sea level is real but small, contributing a fraction of the natural background radiation every person absorbs over a lifetime. In deep space, there is no magnetic field and no atmosphere. A spacecraft in interstellar space receives the full unattenuated flux of galactic cosmic rays from every direction. This is already a known problem for long-duration space missions within our solar system. Astronauts on the International Space Station receive a significantly elevated radiation dose compared to people on the ground, and that station is still partially protected by Earth's magnetic field. Missions to Mars and beyond would expose crews to the full interstellar cosmic ray flux for months or years, a concern that NASA has studied extensively. But for a spacecraft at rest or moving slowly, cosmic rays arrive roughly uniformly from all directions. The flux is isotropic, meaning the number of particles arriving per second is approximately the same whether you look forward, backward, up, or down. This isotropy has a practical consequence for shielding. You need protection in every direction. You cannot simply shield the front of the ship and leave the sides and rear exposed. At relativistic speed, the isotropy breaks down. Special relativity predicts an effect called relativistic beaming, sometimes called the headlight effect, when a source of radiation is isotropic in its own rest frame, and you observe it from a frame moving at high velocity. The radiation appears concentrated in the forward direction. Particles that were arriving uniformly from all directions are now arriving predominantly from the front. The faster you move, the more extreme the beaming becomes. At 50% of light speed, a significant majority of cosmic rays appear to come from a forward cone. At 90%, almost all of them are compressed into a narrow beam ahead of the ship. In one sense, this is helpful. It means that at very high speeds, the cosmic ray flux becomes directional, and a forward shield can block most of it. You no longer need to surround the entire ship with heavy shielding. A thick frontal barrier handles the bulk of the dose, but there is a cost. The beaming does not just redirect the cosmic rays, it also increases their apparent energy. In the ship's reference frame, the cosmic rays arriving from ahead are blue-shifted, their energies boosted by the relative motion between the ship and the rest frame of the galaxy. A cosmic ray proton that carries 1 billion electron volts in the galactic rest frame arrives at a ship moving at 90% of light speed, with an apparent energy several times higher, depending on the angle of arrival and the exact velocity. The most energetic cosmic rays, those already carrying trillions of electron volts, are boosted further still. This means the forward shield must handle not only a higher flux rate, since most of the radiation is now arriving from one direction, but also a higher average energy per particle. Higher energy particles penetrate deeper into shielding material. They produce more secondary radiation as they decelerate. They are harder to stop completely. The shield that was adequate against the standard galactic cosmic ray spectrum at rest becomes inadequate against the boosted, beamed spectrum that the ship perceives at relativistic speed. And the cosmic ray flux is arriving on top of the interstellar medium bombardment. The forward shield is already absorbing trillions of hydrogen and helium atoms per second, already dealing with dust grain impacts, already managing the bremsstrahlung field generated by all of those interactions. The cosmic rays add another layer of high-energy particle radiation to an already saturated shielding problem. To understand how serious the cosmic ray problem is in practical terms, it helps to put actual radiation dose numbers on it. Radiation dose to biological tissue is measured in sieverts. A sievert quantifies the biological damage produced by absorbed radiation, weighted by the type of radiation involved. On Earth at sea level, the average person receives roughly 2 to 3 millisieverts per year from all natural background sources combined. That includes cosmic rays that penetrate the atmosphere, radioactive elements in the soil and building materials, and trace radioactive gases in the air. Astronauts aboard the International Space Station, orbiting at roughly 400 kilometers altitude inside Earth's magnetic field, but above most of the atmosphere, receive approximately 150 to 200 millisieverts per year. That is roughly 50 to 80 times the ground level dose. NASA currently limits astronaut career radiation exposure to levels intended to keep lifetime excess cancer risk below a defined threshold, and long-duration station missions already push against those limits. In interstellar space, outside any planetary magnetic field, the unshielded cosmic ray dose is significantly higher than what astronauts experience in low Earth orbit. Estimates vary depending on the assumed cosmic ray flux and energy spectrum, but a baseline figure for unshielded interstellar exposure is in the range of 400 to 600 millisieverts per year. That alone, without any contribution from the interstellar medium bombardment, would accumulate to a dose of roughly 16 to 24 sieverts over a 40-year journey at a modest fraction of light speed. For reference, a whole body dose of approximately 5 sieverts delivered over a short period is considered lethal to most humans without medical intervention. Even a single sievert accumulated over a working lifetime significantly raises the risk of fatal cancer, and the relationship between dose and risk is roughly linear, meaning each additional sievert adds proportionally more danger. Now layer the relativistic beaming effect on top of this baseline. At high speed, the cosmic rays are not only redirected forward but also blue-shifted in energy. The effective dose rate in the forward-facing direction climbs, and the biological damage per particle increases because higher energy particles produce denser ionization tracks in tissue, which are more destructive per unit of energy deposited. The exact increase depends on the ship's velocity and the specifics of the shielding geometry, but at 50% of light speed, the forward cosmic ray dose rate could be several times the stationary interstellar baseline. At 90%, the multiplication factor grows further. And this cosmic ray dose is being absorbed by crew members who are simultaneously receiving the continuous secondary radiation dose from interstellar medium bombardment of the forward shield, plus whatever direct particle radiation penetrates the shield entirely. The total dose rate is the sum of all contributions. No single source may be lethal on its own at more moderate speeds, but the combination of all sources, cosmic rays, interstellar medium secondaries, dust impact radiation bursts, pushes the cumulative exposure toward levels that challenge any realistic mission duration. Now consider the cosmic microwave background. The cosmic microwave background is the faint thermal radiation left over from the early universe, emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. It fills all of space uniformly, arriving from every direction at a temperature of about 2.725 Kelvin, just above absolute zero. Its peak frequency falls at roughly 160 gigahertz, firmly in the microwave band, with each photon carrying less than 1,000th of an electron volt. By any human standard, it is among the most harmless forms of radiation in the universe. It passes through your body constantly and does nothing. At relativistic speed, the cosmic microwave background is no longer harmless. The same relativistic beaming that concentrates cosmic rays forward also affects photons. The cosmic microwave background photons arriving from ahead of the ship are blue-shifted to higher frequencies and higher energies. The photons arriving from behind are red-shifted to lower frequencies and lower energies. The result is that in the ship's reference frame, the formerly uniform glow of the cosmic microwave background becomes an intensely concentrated beam of high-frequency radiation streaming directly at the forward face of the spacecraft. The degree of blue shift depends on the ship's velocity and the angle of arrival. For a photon arriving head-on from directly ahead, The blue shift factor is gamma times 1 plus beta, where beta is the ship's velocity as a fraction of light speed, and gamma is the Lorentz factor. At 50% of light speed, gamma is about 1.155, and the blue shift factor for head-on photons is approximately 1.73. The peak frequency of the cosmic microwave background shifts from 160 GHz to about 277 GHz. Still microwaves, still low energy, no significant hazard. At 90% of light speed, gamma is about 2.29, and the blue shift factor for head-on photons rises to approximately 4.36. The peak frequency shifts to roughly 700 GHz, pushing into the far infrared. The individual photon energy is still small. The radiation is warming slightly, but not dangerous in itself. At 99% of light speed, gamma is about 7.09. The blue shift factor is approximately 14.1. The peak frequency is now above 2000 GHz, solidly in the infrared. The photon energy has increased by more than an order of magnitude. Still not ionizing, still not directly lethal, but the total energy flux has increased dramatically because the beaming effect concentrates photons that were arriving from all directions into a forward cone, and each photon carries more energy. At 99.9% of light speed, gamma is about 22.4, and the blue shift factor exceeds 44, pushing the peak frequency into the near infrared. At even higher fractions, the cosmic microwave background photons shift into the ultraviolet, then the X-ray range, then ultimately into gamma rays. At extreme Lorentz factors in the hundreds or thousands, the cosmic microwave background becomes a lethal gamma ray searchlight aimed directly at the ship. It is important to be precise about where the real danger threshold lies. For a crewed mission traveling at 50 to 90% of light speed, which is the range most seriously discussed for interstellar travel, the cosmic microwave background blue shift does not produce lethal radiation on its own. The photon energies at these speeds remain below the ionizing threshold. The primary hazard from the cosmic microwave background at these velocities is thermal, not radiological. The concentrated, blue-shifted photon bath deposits heat on the forward surface of the ship, adding to the thermal load from interstellar medium impacts, and increasing the total amount of energy the ship must radiate away to avoid overheating. At the extreme upper end of conceivable velocities, above 99.9% of light speed, the cosmic microwave background does become a radiation hazard in its own right. But these speeds are so far beyond any currently proposed propulsion technology that the practical relevance is limited to theoretical analysis. The important point for realistic mission planning is that the cosmic microwave background contributes to the forward thermal load at any relativistic speed, and becomes progressively more significant as speed increases, adding one more term to an already overwhelming energy balance problem. And that energy balance problem, the thermal problem, deserves its own careful treatment. Every form of energy deposited on the forward surface of the spacecraft must go somewhere. The kinetic energy of impacting gas atoms is converted to heat and radiation. The kinetic energy of dust grain impacts is converted to heat and radiation. The blue-shifted cosmic microwave background deposits thermal energy. Cosmic ray impacts deposit energy. Bremsstrahlung from particle deceleration inside the shielding deposits energy. All of this heat accumulates on and within the forward structure of the ship. On Earth, getting rid of unwanted heat is straightforward. You use convection, circulating air or water, that carries heat away from the hot surface. You use conduction, transferring heat through solid connections to a cooler reservoir. You use evaporation, exploiting the phase change of a liquid to remove large amounts of energy. In space, none of these options work. There is no air, there is no external reservoir. There is nothing to conduct heat into. The only mechanism for shedding heat in vacuum is radiation. The ship must emit infrared photons from its surface, carrying energy away as electromagnetic radiation. This is governed by the Stefan-Boltzmann law, which says the total power radiated per unit area of a surface is proportional to the fourth power of the surface temperature. This means the ship can radiate heat faster if its surface is hotter, but the ship's structure has temperature limits. The whole material softens, weakens, and eventually melts at temperatures that depend on its composition. Aluminum melts at about 660 degrees Celsius. Titanium alloys fail structurally well below their melting point of roughly 1,660 degrees Celsius. Even advanced ceramics and refractory metals have upper temperature limits that cannot be exceeded without compromising structural integrity. The ship must therefore maintain its forward surface below the structural failure temperature of its hull material, while radiating away all the energy being deposited by particle bombardment. Dust impacts, blue-shifted photons, and secondary radiation. If the rate of energy deposition exceeds the rate of radiative cooling, the surface temperature climbs. If it climbs above the material's safe operating temperature, the hull weakens. If it weakens enough, it fails. Research by Huang and colleagues calculated the equilibrium surface temperature of a relativistic spacecraft as a function of speed, accounting for collisional heating by interstellar gas. Their results show that at 20% of light speed, the equilibrium temperature of the forward surface is elevated but manageable for most candidate materials. At higher speeds, the equilibrium temperature rises sharply. The exact temperature depends on the material's emissivity, its ability to radiate heat, and the local density of the interstellar medium. But the general trend is clear. Faster travel means more energy deposited per second, which means higher equilibrium temperature, which means the ship approaches the structural limits of its hull material sooner. Let us make this concrete with a specific scenario. Consider a spacecraft traveling at 30% of light speed, a velocity sometimes proposed as a practical lower bound for interstellar travel within a human lifetime. At this speed, the equilibrium surface temperature of the forward face, the temperature at which the rate of energy deposition from particle bombardment exactly balances the rate of radiative heat loss from the surface, depends on the density of the interstellar medium encountered and the emissivity of the hull material. For a hull made of a high emissivity material, meaning it radiates heat efficiently, traveling through a region of average interstellar medium density, the equilibrium temperature at 30% of light speed is elevated, but likely remains below a few hundred degrees Celsius. This is within the operating range of many structural materials. Aluminum would be stressed, but functional. Titanium would handle it comfortably. Advanced ceramics would be well within their limits. But raise the speed to 50% of light speed, and the thermal picture changes sharply. The energy deposited per second scales with approximately the cube of the velocity in the non-relativistic approximation, and faster still when relativistic corrections are included. Doubling the speed from 25 to 50% does not double the heat load. It increases it roughly eightfold or more. The equilibrium temperature climbs correspondingly. At 50% of light speed through average density interstellar medium, the forward surface temperature could reach several hundred to over 1,000 degrees Celsius, depending on the material properties and the local gas density. At 1,000 degrees Celsius, aluminum is liquid. Most structural adhesives and sealants have long since failed. Titanium is approaching the range where its strength degrades significantly. Only refractory metals like tungsten, which melts at over 3,400 degrees Celsius, and certain advanced ceramics remain structurally sound. But refractory metals are extremely dense and heavy. Tungsten has a density of roughly 19.3 grams per cubic centimeter, almost 2.5 times denser than steel. Using it for the forward shield adds enormous mass, which feeds directly into the fuel penalty imposed by the rocket equation. And if the ship passes through a region of locally enhanced interstellar medium density, a denser cloud or filament, the energy deposition rate spikes. The equilibrium temperature jumps. A surface that was stable at 900 degrees in average density space might surge past its material limit in a denser region, with no warning and no time to react. The ship cannot slow down quickly enough to reduce the heating rate before damage occurs. This is why the thermal problem is not simply an engineering constraint. It is a survivability threshold. There exists a speed above which no known material can maintain structural integrity on the forward face for the duration of an interstellar crossing, even under the most optimistic assumptions about emissivity and interstellar medium density. That threshold depends on the specific mission profile, but it adds one more ceiling to the stack of limits that collectively define how fast a crewed ship can travel and survive. One response to this thermal challenge is to increase the surface area of the ship's radiators. Larger radiating surfaces can shed more total heat per second at a given temperature. But radiators are structures that extend away from the ship's body, and they are vulnerable. They must be strong enough to survive the mechanical stresses of acceleration and deceleration. They must be positioned away from the forward face, where they would be exposed to the full bombardment, and they add mass. Every square meter of radiator surface adds kilograms of structural material that must itself be accelerated to relativistic speed and decelerated at the destination. And this leads directly to what may be the most merciless constraint in all of relativistic mission design: the shielding mass problem. Every kilogram of shielding added to the forward face of the ship provides additional protection against particle bombardment, dust erosion, radiation, and thermal flux. More shielding is always better for survival, but every kilogram of shielding is also a kilogram of mass that the propulsion system must accelerate to cruising speed and decelerate at the destination. The energy required to accelerate mass to relativistic speed is enormous. As we have already seen, the energy required to decelerate it is equally enormous, and the fuel required to provide that energy has mass of its own, which must also be accelerated. This is the rocket equation, the most unforgiving relationship in all of space propulsion engineering. The rocket equation says that the ratio of the ship's initial mass, including fuel, to its final mass after the fuel is spent, grows exponentially with the desired change in velocity. For a mission that must accelerate to a high fraction of light speed, and then decelerate to rest at the destination, the mass ratio becomes staggering. Every additional kilogram of shielding added to the payload multiplies the total fuel requirement by a factor that itself depends exponentially on the mission velocity. This creates a vicious cycle. More shielding improves survival odds, but more shielding increases mass. Increased mass demands more fuel. More fuel adds more mass. More mass demands even more fuel. The exponential growth of the rocket equation amplifies the effect until you reach a point where adding 1 more kilogram of shielding requires hundreds or thousands of additional kilograms of fuel to carry it. The result is that for any given propulsion technology, there is a practical ceiling on how much shielding you can carry. Beyond that ceiling, the ship becomes too massive to accelerate to the required speed with any feasible amount of fuel. Below that ceiling, the shielding may not be adequate to survive the journey. The window between these two limits, sufficient shielding and feasible mass, may be narrow. For some velocity ranges, it may not exist at all. This is the shielding paradox. The protection the ship needs to survive relativistic travel directly competes with the propulsion requirements that make relativistic travel possible. Making the ship safer makes it harder to fly. Making it light enough to fly makes it harder to protect. And shielding is not the only mass that competes for the propulsion budget. The crew habitat has mass. The life support systems have mass. The food and water supply has mass. The medical equipment, the power systems, the communication array, the navigation instruments, all of it has mass. And every kilogram of every system is subject to the same exponential penalty imposed by the rocket equation. For a crewed interstellar mission, the total mass that must be accelerated to relativistic speed and decelerated at the destination is measured in hundreds of metric tons at minimum, probably thousands. Providing adequate shielding against the full suite of relativistic hazards, particle bombardment, dust erosion, cosmic ray flux, thermal loading, secondary radiation, could easily require hundreds of additional metric tons of dense material on the forward face alone. The total mass budget becomes an exercise in compromise where every compromise carries survival consequences. Less shielding to save mass means higher radiation dose and faster hull erosion. Less fuel to save mass means lower cruising speed, which means longer exposure time to the interstellar medium, which partially offsets the benefit of reduced bombardment intensity. Less payload mass means fewer redundant systems, less food, fewer crew, smaller margins for error. There is no configuration that solves all the problems simultaneously. There is only an optimization surface on which every point involves accepting a specific set of risks in exchange for a specific set of capabilities. And across much of that surface, the risks are severe. Now, let us turn to a hazard that operates on entirely different principles from particle impacts and radiation, but is equally lethal. The problem of detection and navigation at relativistic speed. A spacecraft traveling at 10% of light speed covers approximately 30,000 kilometers every second. At 50% of light speed, that rate climbs to 150,000 kilometers per second. At 90%, roughly 270,000 kilometers per second. These are speeds at which the distance from the Earth to the Moon is crossed in 1 to 5 seconds. At these velocities, the ship's ability to detect objects in its path and react to them is governed by the speed of light itself, and the speed of light is not fast enough. Consider a small object, a rock the size of a fist, drifting in interstellar space directly ahead of the ship. The ship's sensors can only detect this object when light reflected from it, or emitted by it reaches the ship's instruments. In the cold of interstellar space, a small rock emits almost no radiation of its own. It is dark, cold, and essentially invisible against the background of space. If it reflects starlight, the reflected signal from an object a few centimeters across is so faint that no realistic sensor could detect it at any useful range. Suppose optimistically that the ship's sensors could detect such an object at a range of 1,000 kilometers. At 10% of light speed, the ship crosses 1,000 kilometers in about 3/100ths of a second, 33 milliseconds. That is less than the duration of a single human heartbeat. At 50% of light speed, the crossing takes about 7 milliseconds. At 90%, roughly 4 milliseconds. In that time, the ship must detect the object, determine its position and trajectory relative to the ship, calculate an evasion maneuver, and execute that maneuver by physically altering the ship's course. The detection and computation might conceivably be done by automated systems in milliseconds, though even that is optimistic for the faint signals involved. But the physical maneuver is impossible. A ship with a mass of thousands of metric tons, traveling at a significant fraction of light speed, has momentum so enormous that changing its trajectory by even a fraction of a degree requires forces that no conceivable thruster system could deliver in milliseconds. The ship cannot swerve. It cannot dodge. It cannot jink out of the way. Its course is effectively fixed over the timescales relevant to collision avoidance with small objects. This means that for objects below a certain size, the ship is blind and helpless. It will hit whatever is in its path with no warning and no recourse. The only defense is statistical. In the interstellar medium, small objects are rare. The average density of significant debris is extremely low. The probability of hitting a fist-sized rock on a 4 light-year journey might be very small, but it is not zero. And the consequence of a single such collision at relativistic speed would be catastrophic, far beyond the capability of any forward shield to absorb. Larger objects, asteroids, comets, rogue planets could potentially be detected at longer range, perhaps light hours or light days ahead. At those distances, the ship would have minutes or hours to adjust course, but maneuvering at relativistic speed requires altering the velocity vector of an enormously massive ship, which requires significant thrust applied over significant time. Even a modest course change of a fraction of a degree demands a burn that consumes fuel that was budgeted for the cruise phase and the deceleration burn. Every evasion maneuver draws from the same finite fuel supply that the ship needs to slow down at the destination. And the detection problem is compounded by a relativistic optical effect. At high speed, the apparent positions of stars and other light sources shift forward in the ship's field of view due to aberration. Stars that are actually to the side or even slightly behind the ship appear to crowd toward the forward direction. The star field compresses into a ring around the direction of travel, distorting the familiar patterns that navigators rely on. At very high speeds, almost all visible light is crowded into a small forward cone, and the rest of the sky goes dark. Identifying individual stars for navigational reference becomes progressively harder as speed increases. The ship is not just blind to small objects ahead. It is also losing its ability to determine precisely where it is and where it is pointing. Navigational precision over interstellar distances is critical. The destination star system is a tiny target at the end of a journey measured in trillions of kilometers. A navigational error of 1 arcsecond, 1/3600th of a degree, sustained over a 4 light-year journey corresponds to a positional error at the destination of roughly 200 million kilometers. That is greater than the entire distance from the Earth to the Sun. An error that's small would mean missing the intended approach trajectory entirely, arriving in the wrong part of the star system with no fuel reserves to correct the mistake. Maintaining navigational accuracy of this order requires continuous position fixes using stellar references, and those references are being distorted by aberration, blue-shifted in frequency, and compressed into a crowded forward cone that makes individual star identification harder. The navigation systems must correct for all of these relativistic distortions in real time, using instruments that have been subjected to years of particle bombardment, radiation damage, and thermal stress, maintained by systems that are drawing from the same limited power and mass budget as everything else on the ship. Everything connects back to speed. The speed that shortens the journey creates the particle bombardment. The bombardment demands shielding. The shielding adds mass. The mass demands more fuel. The fuel adds more mass. The speed distorts the starfield, complicating navigation. The speed makes collision avoidance impossible for small objects. The speed heats the forward hull. The heat demands radiators. The radiators add mass. Every solution to one problem feeds into another problem, and the common multiplier is always velocity. This interlocking web of constraints has led some researchers to suggest that there may be a practical speed ceiling for crewed interstellar travel that is well below the theoretical maximum. Not the speed of light, which is unreachable for any massive object. Not even 90 or 95% of light speed, which would be ideal for minimizing travel time. Perhaps something closer to 10 to 20% of light speed, where the particle bombardment is survivable with heavy shielding, the radiation dose is manageable, the thermal load can be radiated, and navigational precision can be maintained with available technology. At those speeds, the journey to Alpha Centauri takes 20 to 40 years instead of 5, still within a human lifetime, still extraordinarily demanding, but possibly within the bounds of what engineering could achieve without violating any physical limits. Even at these more modest velocities, every hazard we have discussed still applies. The interstellar medium still bombards the hull. Dust grains still erode the surface. Cosmic rays still penetrate the shielding. Heat still accumulates on the forward face. Navigation still requires extraordinary precision. The problems do not vanish at lower speeds. They merely shrink to levels that might, with sufficient design care and acceptable risk, be survivable. But the ship has not yet addressed the problem that bookends the entire journey, and in many ways determines whether the mission is possible at all. It has not addressed how it gets up to cruising speed in the first place, and more critically, how it stops when it arrives. Acceleration and deceleration are not simply the beginning and end of the flight. They are survival problems in their own right, each one carrying physical demands that compound on top of everything the ship must endure during the cruise phase. And the fuel, the mass, the time, and the human tolerance required for these phases may ultimately be the factors that determine whether near light speed travel is achievable, impractical, or simply impossible for a crewed mission. How those phases work, what they demand, and why they close the final loop on the paradox of relativistic travel is what remains. Before a ship can face the gauntlet of dust, gas, radiation, and heat that fills interstellar space at relativistic speed, it must first reach that speed. And reaching that speed is not a simple matter of firing the engines and waiting. It is a survival problem in its own right, governed by the limits of the human body, the tyranny of the rocket equation, and the sheer physical reality of what it means to push a massive object to a significant fraction of the speed of light. Start with the human body. Acceleration is felt as a force. When a car accelerates, you're pressed into your seat. When an elevator starts upward, you feel heavier. This sensation is the force of acceleration acting on your body, and your body has limits for how much of it you can tolerate and for how long. The standard unit for acceleration tolerance is the g, defined as the acceleration due to Earth's gravity at the surface, approximately 9.8 meters per second squared. Standing on Earth, you experience 1g continuously. Your body is designed for it. Your cardiovascular system, your skeletal structure, your inner ear balance mechanisms, all of them evolved under 1g and function best at 1g. At 2g, you feel as though you weigh twice your normal weight. Sustained 2g acceleration is uncomfortable, but tolerable for healthy adults over periods of hours. Fighter pilots routinely experience brief bursts of 6 to 9g during high-performance maneuvers, but only for seconds at a time, wearing specialized compression garments to prevent blood from pooling in their lower extremities. Without those garments, sustained acceleration above 4 to 5g drains blood from the brain, and blackout occurs within seconds. For a long-duration interstellar mission, the crew cannot wear pressure suits for months or years. They need to live, work, eat, sleep, and function normally during the acceleration phase. This limits sustained acceleration to a level the human body can handle continuously over extended periods. Most studies place this limit at approximately 1g, possibly 1.5g, for shorter acceleration phases of weeks to months. Beyond that, the physiological burden becomes unacceptable for continuous exposure. Bone stress, cardiovascular strain, fatigue, impaired mobility, all of these accumulate under sustained high G conditions and degrade the crew's ability to operate the ship. So let us assume 1g of sustained acceleration. That is the most comfortable option, replicating the gravitational environment the crew evolved in. At 1g, how long does it take to reach a significant fraction of light speed? The math is straightforward in the non-relativistic approximation. At 1g, you gain approximately 9.8 meters per second of velocity every second. After 1 hour, you're traveling at about 35 kilometers per second. After 1 day, roughly 850 kilometers per second. After 1 year of continuous acceleration at 1g, you would reach approximately 300 million meters per second, which is almost exactly the speed of light. But of course, you cannot actually reach the speed of light because the relativistic correction intervenes. As the ship accelerates and approaches the speed of light, each additional unit of thrust produces a diminishing increment of velocity. The ship gets heavier from the perspective of the energy required to accelerate it further. The Lorentz factor resists the acceleration, bending the velocity curve asymptotically toward, but never reaching the speed of light. In practice, 1 year of sustained 1g acceleration as measured on Earth gets you to a very high fraction of light speed, roughly 72% according to relativistic calculations. To reach 90% requires somewhat longer. To reach 99% requires significantly longer still, and each additional fraction demands disproportionately more time and energy. But let us focus on a more modest target. Suppose the mission plan calls for a cruising speed of 50% of light speed. At 1 g of sustained acceleration, reaching 50% of light speed takes approximately 200 days, roughly 6.5 months. During those 6 months, the engines must fire continuously, never stopping, never faltering. The thrust must be precise and consistent. The fuel must flow without interruption. The structural integrity of the ship must withstand 6 months of continuous mechanical stress from the drive system. 6 months of unbroken engine operation is already far beyond anything humanity has ever attempted with a high-thrust propulsion system. Chemical rockets burn for minutes. Even ion drives, which are designed for long-duration operation, have duty cycles measured in months, with planned pauses for maintenance and course adjustment. A 6-month continuous burn at 1 g with a propulsion system powerful enough to accelerate a crewed interstellar spacecraft is an engineering challenge of an entirely different order. And the fuel required for that burn is where the rocket equation transforms a difficult challenge into a potentially impossible one. The rocket equation, first published by Konstantin Tsiolkovsky in 1903, describes the fundamental relationship between a rocket's exhaust velocity, its fuel mass, and the velocity change it can achieve. In its simplest form, the equation says that the velocity change, or delta V, a rocket can achieve is equal to the exhaust velocity of its propellant, multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. The natural logarithm is what makes this equation merciless. It means that the relationship between fuel mass and velocity change is exponential. To double the delta V, you do not double the fuel. You square the mass ratio. To triple the delta V, you cube it. For the enormous velocity changes required by interstellar travel, the mass ratios become absurd. Consider a ship that needs to accelerate to 50% of light speed. That is a delta V of 150,000 kilometers per second. Now consider the best propulsion technologies that have been seriously proposed for interstellar travel. An advanced nuclear pulse propulsion system using fusion rather than fission detonations might achieve exhaust velocities of roughly 1,000 to 10,000 kilometers per second, depending on the design. A fusion drive, if one could be built, might reach exhaust velocities in the range of 10,000 to 30,000 kilometers per second. Even an idealized antimatter annihilation drive, converting fuel mass directly into a directed photon exhaust, would have an effective exhaust velocity approaching, but never exceeding the speed of light itself. For a nuclear pulse drive with an exhaust velocity of 3,000 kilometers per second, the mass ratio required to achieve a delta V of 150,000 kilometers per second is a raise to the power of 50. That number is approximately 5.18 times 10 to the 21st power. For every kilogram of payload, including the ship, the crew, the shielding, the life support, and everything else, you need more than 5 billion trillion kilograms of fuel. For a ship with a payload of just 1 metric ton, the fuel required would roughly equal the mass of the entire Earth. A fusion drive with an exhaust velocity of 20,000 kilometers per second improves the picture. The mass ratio drops to E raised to the power of 7.5, which is approximately 1,800. For every kilogram of payload, you need 1,800 kilograms of fuel. A ship with a dry mass of 1,000 metric tons would require 1.8 million metric tons of fusion fuel. This is conceivable in the most generous sense, not with current technology, but not obviously forbidden by physics. It is at the outer edge of what future civilizations might manage. an idealized antimatter drive fares best. With exhaust velocity approaching the speed of light, the mass ratio for a delta V of 50% of light speed drops to roughly the square root of 3, about 1.73. For every kilogram of payload, you need less than 1 kilogram of antimatter fuel. This sounds almost manageable until you remember that the total quantity of antimatter ever produced by all the particle accelerators on Earth combined is measured in nanograms, that antimatter costs roughly $62 trillion per gram at current production rates, and that storing more than a few atoms of it without annihilation is at the very frontier of laboratory capability. And every one of these calculations covers only the acceleration phase. The ship still needs to stop. This is the deceleration problem, and it is every bit as demanding as acceleration. A ship arriving at Alpha Centauri at 50% of light speed must shed that velocity entirely, or nearly so, to enter orbit or rendezvous with the planetary body. Shedding velocity requires applying thrust in the opposite direction for an equal duration and with an equal energy expenditure. For a rocket-propelled ship, this means carrying enough fuel not just to accelerate, but also to decelerate. The fuel for deceleration is payload during the acceleration phase, meaning it must itself be accelerated. And the fuel required to accelerate the deceleration fuel must also be carried and accelerated. And that fuel needs its own fuel. And the exponential cascade of the rocket equation applies again, compounding on top of the already extreme acceleration requirement. For any propulsion system that carries its own fuel, the mass ratio for a mission that must both accelerate and decelerate is not twice the one-way ratio. It is the one-way ratio squared. If the one-way ratio for a fusion drive is 1,800, the round-trip ratio, acceleration plus deceleration, is 1,800 squared, which is 3.24 million. For every kilogram of payload, you need 3.24 million kilograms of fuel. A 1,000 metric ton ship requires 3.24 billion metric tons of fusion fuel. These numbers illustrate why some interstellar mission concepts propose using external propulsion for the acceleration phase. A ground-based or space-based laser array pushes the ship with a beam of light, so the ship carries no acceleration fuel. This is the principle behind the breakthrough starshot concept. But if the ship carries no propulsion of its own, it cannot decelerate at the destination. It does a flyby, passing through the target system at cruising speed and continuing into deep space. For an uncrewed probe, a flyby provides a brief window for observation and data collection. For a crewed mission, a flyby is useless. The crew must stop. Alternative deceleration methods have been proposed. Magnetic sails interacting with the destination star's stellar wind. Light sails using the star's radiation pressure. Aerobraking in a planetary atmosphere, though approaching a planet at a significant fraction of light speed carries its own catastrophic risks. Each of these methods has severe limitations. Magnetic sails require a strong stellar wind, which varies enormously between different types of stars. Red dwarf stars like Proxima Centauri have weaker and more variable stellar winds than sun-like stars. Light sails work only when the ship is close enough to the destination star for the radiation pressure to be significant, which means the ship must already be in the star system and moving slowly enough to maneuver. Aerobraking at relativistic speed would compress the atmospheric gas ahead of the ship to extreme temperatures and pressures, turning the atmosphere itself into a plasma barrier that would incinerate any known material. The deceleration problem has no clean solution. Every approach requires either enormous fuel reserves, which drive mass ratios to impractical levels, or reliance on external forces at the destination, which may not be available, predictable, or sufficient. And here is where a seductive idea enters the conversation, one that many popular treatments of interstellar travel lean on heavily: time dilation. Special relativity predicts that time passes more slowly for an object in motion relative to a stationary observer. The faster the object moves, the greater the effect. At 50% of light speed, the Lorentz factor is approximately 1.155, meaning time aboard the ship passes about 13% slower than time on Earth. At 90%, the factor is about 2.29, and the crew experiences roughly 44% as much time as Earth observers. At 99%, the factor is about 7, and the crew ages at 1/7 the rate of those they left behind. Time dilation is real. It has been confirmed experimentally with atomic clocks on aircraft, on satellites, and in particle accelerators. It is not speculative. It is not approximate. It is a precise, measured consequence of special relativity that applies to every object in motion. And it is tempting to believe that time dilation solves the problem. If the crew experiences fewer years during the journey, then perhaps the hazards are reduced proportionally. Fewer years of radiation exposure, fewer years of particle bombardment, fewer years of psychological strain in confinement. But this reasoning contains a critical error. Time dilation reduces the crew's subjective experience of the journey's duration. It does not reduce the physical interactions between the ship and its environment. The number of hydrogen atoms the ship encounters during its crossing of interstellar space depends on the distance traveled and the density of the medium, not on the subjective time elapsed aboard the ship. A ship traveling 4.24 light years through an interstellar medium with an average density of 1 atom per cubic centimeter sweeps through the same total number of atoms regardless of whether the crew experiences that journey as 5 years or 5 months. The total radiation dose from particle bombardment depends on the total number of impacts, not on the crew's perception of time. The total dust erosion depends on the total number of dust grains encountered, not on whether the crew was aging quickly or slowly while the erosion occurred. The total heat deposited on the forward hull depends on the total energy of all impacts, not on the subjective clock rate aboard. Time dilation compresses the crew's experience of these hazards into a shorter subjective window, but it does not reduce their magnitude. In fact, by enabling higher speeds, time dilation is correlated with more intense hazards per unit of distance traveled. A ship moving at 90% of light speed experiences time dilation of roughly a factor of 2, but each hydrogen atom strikes with billions of electron volts instead of millions. The crew ages more slowly, but the ship is hit harder per meter of travel. There is no free lunch in physics. Time dilation does not make near light speed travel safer. It makes the extreme dangers pass more quickly from the crew's perspective, while leaving the total physical punishment unchanged or worse. And now we can see the full shape of the paradox. The stars are far away, unimaginably, crushingly far away. The distance between solar systems is measured in trillions of miles, in light years, in units of distance so large that they reduce every human accomplishment to an imperceptible dot. The only way to cross that distance within anything resembling a human lifetime is speed. Enormous, relativistic speed. speed measured in significant fractions of the fastest thing in the universe. And the universe provides that speed, in principle. The laws of physics do not forbid a spacecraft from reaching 50, 70, 90% of the speed of light. There is no wall at any particular velocity below light speed. No law that says a ship must stop at 10% or 20%. The energy requirements are extreme but finite. The engineering is beyond current capability, but not beyond the boundaries of physics. With sufficient energy, sufficient fuel, sufficient engineering sophistication, a spacecraft with mass could in principle accelerate to 99% of the speed of light and cross the distance to the nearest star in a journey that its crew would experience as a matter of months. But the universe does not give that speed for free. It charges a price, and the price is not measured in fuel alone. Every increment of velocity purchased loads the spacecraft with kinetic energy that transforms every encounter with the interstellar medium into a violent event. Every atom of hydrogen in the ship's path becomes a relativistic projectile. Every dust grain becomes an explosive. Every photon of the cosmic microwave background gains energy. Every cosmic ray is boosted and beamed into the forward shield. The shielding required to survive these encounters adds mass that makes the ship harder to accelerate and harder to decelerate. The heat generated by the bombardment must be radiated away through surfaces that add more mass. The fuel required to move that mass follows the exponential demands of the rocket equation, multiplying the ship's initial mass to impractical levels. The acceleration phase stresses the crew and the structure for months. The deceleration phase demands an equal expenditure of energy and time, doubling the fuel requirement. The navigation systems are blinded and distorted by relativistic effects. The sensors cannot detect small hazards in time to avoid them. Time dilation does not reduce the physical toll, only the crew's awareness of how long it lasts. The faster the ship moves, the more efficiently it closes the distance, and the faster it moves, the more hostilely the distance fights back. This is the reversal of expectation that sits at the heart of near light speed travel. Speed is supposed to be the answer. Speed is what makes the journey conceivable, what shrinks light years to manageable durations, what transforms the gap between stars from an impossible chasm to a difficult crossing. Every popular vision of interstellar travel treats speed as the solution and distance as the problem, but the physics tells a different story. Distance is passive, it just sits there, enormous and indifferent. Speed is active. Speed is what changes the environment around the ship. Speed is what transforms a harmless wisp of interstellar gas into a continuous particle beam. Speed is what turns microscopic dust into projectiles with the energy of munitions. Speed is what boosts the cosmic ray flux, heats the hull, overwhelms the shielding, blinds the sensors, and demands exponentially more fuel for every increment gained. The space between the stars is not a passive void waiting to be crossed. At relativistic velocity, it becomes one of the most dangerous environments in the known universe, not because it contains anything unusual, but because it contains anything at all. At low speed, 1 atom per cubic centimeter is nothing. At near light speed, 1 atom per cubic centimeter is a storm. And the emptiness itself is part of the cruelty. In a dense environment, an asteroid belt, a planetary atmosphere, you can see the danger. You can map it, model it, avoid it. The interstellar medium offers none of those options. The danger is invisible, diffuse, uniform, and inescapable. You cannot steer around it because it is everywhere. You cannot wait for a gap because there is no gap. You can only push through it, absorbing the punishment with whatever shielding you carry, radiating the heat as fast as physics allows, and hoping that the statistical improbability of a larger impact holds for the entire duration of the crossing. The word annihilate in the title of this episode is not hyperbole. It is a precise description of what the physics predicts. A human mission traveling at a high fraction of light speed would be subjected to a continuous, unrelenting assault from the medium it passes through, an assault whose intensity scales with the very speed required to make the mission possible. The particles would erode the hull. The radiation would saturate the shielding. The heat would stress the structure. The fuel requirements would strain the limits of any propulsion system. The deceleration would demand as much energy and mass as the acceleration. And the crew, no matter how well protected, would be living inside a vessel that is absorbing the kinetic equivalent of a sustained bombardment for every second of every day of the journey. Near light speed travel would not annihilate a human mission because of some mystical property of the speed of light. It would annihilate it because at relativistic velocity, the kinetic energy of ordinary matter, the energy of dust, gas, photons, the energy that the ship itself carries, becomes so extreme that the physical environment ceases to be survivable by any engineering margin we can currently envision. The universe is not hostile to travelers. It is indifferent. But indifference at relativistic speed becomes indistinguishable from hostility, because the energy scales transform every mundane particle into a threat and every empty mile into a gauntlet. And yet, this does not mean interstellar travel is impossible. It means it is harder than the dream suggests. It means that the first humans to cross the gulf between stars will not do it by outrunning the dangers. They will do it by understanding them so precisely, so completely, so honestly, that they can design for them. Build shielding that can absorb what must be absorbed. Radiate heat that must be radiated. Navigate through distortion. Decelerate with whatever method proves feasible. Accept the risks that cannot be eliminated, and mitigate the ones that can. The danger of near light speed travel is not a reason to abandon the dream of reaching other stars. It is a reason to approach that dream with the seriousness it demands. To stop treating interstellar travel as a simple extension of rocketry and start treating it as the most complex engineering, physics, and survival challenge the human species has ever contemplated. The stars are there. They are real. They have planets. Some of those planets may harbor conditions we would recognize. The distance is enormous, and the speed required to cross it turns the emptiness between those stars into something fierce. But here is what should keep you up tonight. The emptiness was always there. The atoms were always there. The dust was always there. The cosmic microwave background has been glowing at 2.725 Kelvin since 380,000 years after the birth of the universe. None of it changed. None of it moved. None of it became more dangerous on its own. What changed is the speed. What changed is us. What changed is the decision to move fast enough that the ordinary, quiet, invisible contents of interstellar space, material so thin it makes the best laboratory vacuum look dense, become the most lethal environment a human crew could ever enter. The faster a ship moves to survive the distance, the more the distance tries to destroy the ship. That is the paradox. That is the reversal. That is the price the universe charges for crossing the gulf between the stars at anything approaching the speed the universe itself uses to carry light. And the terrifying part is not that the price is too high, it is that the price exists at all, that the solution and the danger are the same thing. That speed is both the key and the weapon. That the emptiness between the stars, the most vacant, the most silent, the most apparently harmless environment in all of nature, becomes lethal not because anything in it changed, but because we dared to cross it fast enough to notice what was always there. Good night.